I'm Konstantin from the University of Kiel, where I most recently became a private docent. And today I will walk you through one of our most recent papers on revisiting the empirical stellar relations. And in particular, we will hear a bit about star spots and what we found out about these star spots and their consequences for example, stellar coronal mass ejections. Now, the increasing sensitivity of ground-based and space-based instruments has led to an exponential growth on the detection and characterization of these bright flashes that occur on the sun and other stars, known as stellar flares. And space missions in particular, like Kepler and TESS, have contributed significantly to our understanding of the statistical properties of the flare energy, but also the flare frequency of cool stars. And what we also have learned, of course, is that superflare stars tend to have larger star spots than what we see on the sun. And in combination with multi-wavelengths observations, for example, the stellar dimming, we now are at the verge, or this opens a new window to search for signatures of space weather, in particular these coronal mass ejections and the particles accelerated along these shock fronts, so stellar cosmic rays. And of course, their impact on planetary atmospheres and thus habitability of the planet, which we are doing in this SPP in our INCREASE team. Now, some of the most important properties of flares and CMEs and SEPs are determined by the strength of the magnetic field and the size of the stellar active region that is associated with star spots and the area of the star spots, which is derived from observations, as we can see here in these left panels. Now, the amplitude of the rotationally modulated brightness variation and the effective stellar temperature, so the photospheric temperature, are directly derived from observations, as shown here, and uses often the Doppler imaging method sketched here on the right-hand side. However, the evaluation of the starspot temperature itself is usually based on an empirical scaling with the effective temperature of the star, which first of all has been introduced by Berdugina in 2005. Based on a stellar sample of 18 cool stars, shown here by these symbols. Now, what you see is the star spot temperature contrast, so delta T, so T star minus T spot, versus the stellar temperature. However, because we measure the stellar temperature, we can also have a direct look at the temperature of the spot itself. Now, Berdugina found that the relation, or both relations, are best described by a second-order polynomial fit to the data, which in principle should be, or should hold true for all types of stars, but in particular for the cool star regime. So when I found this, I was curious on how the sun fits into this picture, and this is what we end up with. And I was a bit surprised by the fact that it's not well represented by this theoretical prediction. So the next natural step for me was to look for further samples that can be added to the picture. And this came as the second surprise because there are only two, one from Biazzo et al. In 2006 and one from Valio in 2016, which are shown here on the left-hand side. Now, a word of caution. Both samples are not based on the method, the Doppler imaging method I talked about before. So in principle, all three samples should be seen more as a typical averaged value that might be underestimated. Now, Valio also proposed an equation to get an idea about the star spot temperature, which basically is a linear relation given by this equation here. However, if you compare both studies, you clearly see that neither of the two empirical correlations is able to reproduce the entire stellar sample. So a more reliable correlation is needed, which we actually did in this paper I'm presenting here. And for the first time, we also, as you can see in both panels, introduced an error band to this fit. And you can see that the sample, or all three samples, are now well represented. And in order to test the validity of our newly derived equation even further, we performed a comparison with the most recent observations that are shown here by these colored diamonds, and this orange line here, as well as the most recent 3D MHD Starsport simulations by Panja et al. 2020. And as can be seen, both the observations and the simulations are remarkably well described. And this is really good news because in particular, this delta T here is often used as a semi-empirical quantity to derive other stellar relations, like, for example, to estimate the star spot areas, the flare energy, and the properties of stellar CMEs. So let's first have a look at the impact on the estimation of the star spot sizes, and this may take a bit. Now, according to Mahehara et al. 2017, the area of the star spot normalized to the area of the solar hemisphere can be described by this equation. So we have everything we need. We have the stellar temperature, we have our delta T from our newly derived equation, and we have this delta F over F star, which is actually the stellar brightness variation normalized by the average stellar brightness that is measured by Kepler-Rain test. So we have everything at hand. Now, one way to show these relations is this diagram right here. So we have the spot group area on the x-axis, we have the flare energy on the left y, and the peak X-ray flare intensity on the right y-axis. And what you see here as these black dots is what the sun is producing, or has been producing, over the last 40-ish years. So we see that small spot group areas tend to produce smaller flares, while bigger spot group areas tend to produce higher energy flares, which comes to no surprise. However, the surprise came in when Yuta Notsu in 2019 released his revised Kepler G-type sample. Here shown are only the sun-like stars, so which should be comparable to what the sun is doing. And you can see this is a bit off. And this is still under investigations whether or not the sun is a typical G-type star or not. However, what I want to mention is that Yuta based his analysis on the relation by Vodugina, and if you use our new relation, you can see that there is a shift in the spot group areas about 20% to the right, so going to higher or bigger spot group areas. And this becomes even worse if you look at, or worse or better, how depending on where you look at, from which point you look at. So if you go to K and M stars, so even cooler stars, the difference is about 40%. However, this brings, or this is in better correlation to what the sun is showing here. Now, according to Emsley, also this is based on the sun, the upper limit of the total energy released in a flare can be described as a constant fraction, F, of the magnetic field energy. Thus is a rather simple scaling law depending on a spot, so depending on an empirical quantity. Now, F is a problem in itself because this can vary between 1 and 50% depending on which investigation you look at or which study you look at. However, what we found is that the upper limit of the star spot magnetic field is more likely to be about 2,000 Gauss rather than 3,000 Gauss that have been reported previously, which brings it even closer to what we actually measure at the sun. Now, the total flare energy can further be scaled. So we use what we have learned here based on our A spot, put it in these equations here given by Takahashi et al. 2016. And we can see there is a clear correlation with the flare energy, but also the peak proton flux, which is a crucial, I don't know the English word, a crucial measure for the impact of cosmic rays on the atmosphere of planetary or exoplanetary systems. And by using these new A spot values, we found that in particular for M-type stars, the pre-proton flux most likely was underestimated by about 40%, which is even higher than what we proposed in a study from 2019. So this would mean tremendous proton fluxes around cool stars. Now, this came a bit of a surprise again, and just one brief mentioning. So we are working now, or we had a look in the solar relations again, and found that we also have to update the solar, what we know from the sun. So this upper limit by Takahashi might not be the right one. So it might even be an overestimation. So this 40% might be overestimated. So this is a study we are about to submit next week. And based on what we found out here, we also are working now on a paper about the cool star energy spectra. So this is so I'm at the end of my talk. So just a brief summary. So we proposed this new delta T equation, which has dramatic consequences for spot group areas, but also for the flare energy and the peak proton fluxes. And therewith, I'm at the end, and I hope to get some nice questions. Thank you.